Thank you so much for joining us, and in this session, you will hear from Michael Lebby, who's been the Lightwave Logic's Chief Executive Officer since 2017. Michael earned a doctorate in engineering and holds over 200 issued utility patents. Today, he is joining us to discuss electro-optic polymers. If you have any questions or comments, you can type them right to the conference chat box on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any sort of technical issues throughout the event, please log out and back in to rejoin the session. Michael, we appreciate you for taking the time to present here at the 2023 Photonics Spectra Conference.
Thank you. So I'll get started in my presentation. In the next 20-25 minutes, I'm going to give a quick overview of where we are with electro-optic polymers, and I'll get started. First slide is a safe harbor slide because we are a public company on NASDAQ. And so the next slide really sums it up. We are really excited about this technology. We're excited about the opportunities with the market. And we're also excited because we actually got to NASDAQ a year ago, just over a year ago, and we actually rang the bell as sort of a happy shot with me there, with one of the trophies they give you, and you get your pictures up on Times Square. The rare thing that happened on this was that we had an organic uplist. So that meant that we didn't do a reverse split and we didn't raise any money. So that's very unusual. And NASDAQ just sent us an update that we had our first anniversary. So let's go into the technology. 4 takeaways for the slide. Let's have a look at these. We have unique polymers. Our technology has great performance. It's ultra fast, ultra low power. We are positioned to have these polymers become ubiquitous, a bit like other polymers that you're probably looking at right now, OLEDs, organic LEDs on the mobile phones, monitors, and TVs. And lastly, polymers are foundry and pluggable compatible, which is really exciting. So what are our unique core competencies? Well, the thing about using polymers is that they naturally switch and modulate light very, very quickly. And that's due to the material properties. And that's at least 2 to 3x faster than the existing solutions. They operate at really low power voltages. That's low power consumption. That's like an order of magnitude lower than what you see today. And depending on the device and architectural design, and that's hugely important for the hyperscaling type market. We can fabricate these things quite easily using silicon foundries, and I'll go into that a little bit more in the talk. And we have security of supply. We generate our own materials in Denver, Colorado, and that's scalable in volume. And we are a low-cost addition to integrated photonics platforms. So we have some great, unique properties in our polymers. So let's have a quick look at the market dynamics. Well, this is a slide you may or may not have seen before, but the trends are quite common. If you look at the red boxes, what we can see here is the electricity usage in data centers. And you can see it's rising pretty quickly. Also on the blue boxes I've highlighted, you can see that the traffic is increasing also pretty quickly too. So if you add the traffic and the power, that happens to be a major challenge for data centers and the hyperscalers, as well as the service providers. And really it's the Achilles heel of the industry. How do you deal with these 2 major effects that are going on? And so let's think about the technology we use to address this. Well, a hybrid PIC. What is a hybrid PIC? A hybrid photonic integrated circuit. Well, let's think about this for a second. Fiber communications have 2 incumbent PICs. And one is indium phosphide, which is on the left side of this graph, and the other one is silicon photonics. And we can see at the bottom a lot of merits for these platforms, but they can't do everything. And so pure play materials can't do everything you want. Incumbent technologies can't do everything, at least monolithically. But if you start thinking about adding different types of materials, calling them hybrid PICs, we can do a lot more things. And so whether it's polymers, dielectrics, or even other materials, hybrid PICs can certainly boost the performance of PICs. And if you think about what a hybrid PIC is, it could be indium phosphide and silicon ICs. It could be silicon photonics with indium phosphide, gallium arsenide, and silicon. Also, you can see there are a number of new platforms for hybrid PICs in terms of materials. And there's a list on this graph in the red box, polymers, dielectrics, silica, etc. And there are many others here. The takeaway from this slide is that you have to mix and match to optimize to get the best performance. And this is the direction of the industry right now. And so this is a slide from Yole market research, and you can see it shows the growth of silicon photonics and the trend towards hybrid PIC platforms. And then the question now is what combinations of technology make sense for hybrid PICs? The challenge is to further the PIC performance with different types of materials. So the next question is our technology Foundry compatible? Well, in terms of polymers, certainly we can run it in silicon, indium phosphide, gallium arsenide foundries. And you can see a number of other technologies can also run in the traditional foundries. And as you go through the different types of materials, then you start looking at whether a big silicon foundry is compatible or not. And as you can see from this slide, there's a number of different options and different question marks. Silicon and indium phosphide, from the takeaway standpoint, offer the best opportunities to scale volume quickly and efficiently. So let's have a look at electro-optic polymers. From our standpoint, the Polymer Plus and the Polymer Slot, these are techniques to fabricate electro-optic modulators that are polymer-based onto silicon platforms. You can see the Polymer Plus is a simple approach to putting down the cladding and the core, and the Polymer Slot is approach to doing a very tiny form factor modulator onto silicon photonics. And so one way of looking at this is you could turbocharge your silicon photonics and integrated photonics platforms with electro-optic polymers. Foundry scaling, because you do need to be able to take your technology to the foundry to scale in volume. And so from our standpoint, we need to partner for success. So partnering with foundries and a number of foundries is important for us to get to scale. Also, to partner with packaging partners and partner with module and transceiver partners. And that will position our company for high volume manufacturing. The other things that we have to think about in terms of partnering is licensing and technology transfer. For us, these are important metrics that we have in our business plan. And so the partnering allows us to focus on our uniqueness, our efficient use of capital, and to prepare ourselves for volume manufacturing. And so for us, we're working with a number of different foundries here. You can see the different geographical locations. You can see the type of wafers that are used. The ones in green are active right now. The ones in orange that we are in discussions. And we can see that we're in progress with these, and we have results in the second half of 2022 and first half of 2023. So we have deep activities with foundries for volume scaling. And this is a cross-section of a silicon slot electro-optic polymer modulator. You can see that it is compatible with PDKs that go into the silicon foundries, standard silicon fabrication processes, standard silicon tools. And you can see here where the slot is with the two blue vertical arms, and it's on a silicon photonics and silicon wafer with passivation to protect it. And these are results that we've had back from foundries, which indicates that we're not only using our fab in Denver, Colorado, which is quite small, but we're actually getting modulators back from our foundry partners. And these are standard silicon fabrication components. This is just showing you a vertical grading coupler example, just showing you the quality of the work that the foundries are doing, which is quite impressive. And I'm just showing you on this slide, in terms of foundry process in verniers, we have better than 20 nanometer alignment in our verniers, and it's nice quality work. And also some close-ups of some grading couplers, straight wave guides, strip to slot converters with excellent definition. And so what we look for in terms of working with the foundries is quality of the fabrication, great alignment, and great performance of the results. And so one of the other issues that I want to bring up is polling at foundries. We have unique EO performance of polled polymers. Our polymers you have to poll in order to align the dipoles so we can get the modulation of the light. Polymers are stable and reliable. And the same arguments were actually made against liquid crystal displays and OLEDs. But now if you think about it, we use OLED TVs. We never really discussed the stability and the reliability of polymers in these types of displays. And the same thing applies with our polymers too. And also, lastly, the polling is a process that is consistent, stable, and reliable, and it's quite suitable for Foundry operation. And it's an advanced process from our standpoint. We have excellent control, and it's a standardized technique. And we are in the process of porting polling to Foundries to simplify the PDK processes. So polymers are stable, and the stability of polymers, you can see from this graph, goes out to 5,000 hours. This is just one piece of data I'm showing in this presentation of over 5,000 hours stability, 85 degrees C, and we can see the voltage delta is less than 5% here. And so these types of tests that we are running continuously in our labs, and we'll be presenting more data later this year and earlier next year. Polymer modulators are tiny, and this just shows you the size of a polymer modulator can be 1 millimeter by about 0.5 millimeter. And if you have an array of 1 by 8 of these, which is a CAD design that's going onto our wafers, they are very small. And you can see just by looking at a competitive module on the left, which is a 9 by 15, 1 by 8 array of thin film lithium niobate, you can see on the right that in that space you can fit a lot of modulators because our modulators are really small. In this particular example, you can show in that particular space you can fit 120 of them. In applications, you may not need 120, but what this shows is the potential for at least 30x data capacity because our modulators are so small. So they effectively use the space in an optical transceiver much more efficiently than some of the competition. And size, low power, and speed really matter in these types of applications. So breaking the speed limit, our polymers go really, really fast. And so if you look from a historical perspective, this is a 3D graph that was motivation for the Ethernet Alliance. But you can see here, we started off 1G. In the 90s, we went to 10G. That was sort of pedal to the metal, went a little bit faster. To get to 40, we had to do 4 lanes, a little bit more difficult, as I recall. And then from 40 to 100, we had 4 lanes, and we increased the lane speed to 25. And they got a little bit more difficult when we went to 400G, and we had a couple of different options, whether it was 4 lanes and 8 lanes. And then as we go to 800 and 1600, it gets much more difficult. And so, you know, we're increasing modulation complexity, we're increasing parallelism, but are we really addressing speed? That's the big question here. As we increase the data rates, it's more complex for us. In fact, I try and look at this from a road analogy. I mean, this is, you know, we went from dirt roads to paved roads to freeways. So, I mean, from an internet or an optical network standpoint, more lanes add more traffic capacity. So we did the easy things like paving the road and adding more lanes. And, you know, we've done in our technology, WDM, sending more colors down the fiber. But more symbols per bit, I mean, increasing the coding, is sort of, in my eyes, like stacking cars on top of each other. But we've actually done this as an industry. So we've done the hard stuff like encoding and higher order modulation. But if we really think about the speeds, I know we have speed limits in public roads today, but a lot of the optical devices are still at the same speed. I mean, cars really don't go that much more than 60 miles an hour, even though perhaps they have the potential. Speed has hit a plateau. And so if you think about it by applying that sort of concept to this 3D graph, in optical analog metrics, most optical devices are still running about 35 gigahertz EO S21 bandwidths. And as you try and increase the optical device speeds, it's actually pretty difficult. And in fact, over the last 10 years, we haven't seen a lot of progress here. And so the speed is limited in optical devices by, I guess, the device physics. And there's been a lot of innovation, but not much progress. If you start looking electro-optic polymers, you know, these things run at 100 gigahertz 3dB bandwidths. Unfortunately, some of the equipment we measure them at only goes to 110, so then we have to extrapolate. Super high performance in these types of devices. So what does that mean? That means that polymers can increase the data rates as their bandwidths are 70 gigahertz, 100 gigahertz and beyond, which is really exciting. And so that means that the holy grail, as per the Ethernet Alliance roadmap here, this is a link speed graph versus decades in time. I mean, that red arrow is what they are calling the Holy Grail challenge. Can you do this in a single lane? To us, to Lightwave logic, the way you address that is higher speed optics. And one way of looking at higher speed optics is, can you break through that green dotted line wall with higher speed electro-optic modulators that are very low power? Well, you can look at the yellow sort of box to the right there, and with 100 gigahertz EO S21 3 dB bandwidth, you can get 150 gigabits per second NRZ, that's 150 gigabaud at one lane. And if you want to PAM4 that, then you can take it to 300 gigabits per second. And that's really, really exciting. That allows you to really think more carefully about next generation systems. Ultra fast speed is really exciting. And for us, we're optical engines that go into transceivers, polymer modulators, fabricated in silicon foundries. On the bottom right-hand part of this slide, we have the OSFP, which is a form factor that is getting a lot of attention. It's not the only one, but it is a vehicle where our engines can really fit into. And so if you look at some of the roadmaps we've seen by folks in the systems industry, folks are already talking about 1.6 terabits per second and 3.2 terabits per second optical transceivers. The pluggable transceiver direction is heading where that green arrow is. And so we need to increase the speed in conjunction with the electronics in order to get there. And as we look at this roadmap and we think out what's going to happen over the next decade, I mean, whether we're going to 200 gigabits per second or 400 gigabits per second, these are questions I think the industry needs to ask and answer. But from our standpoint, faster optics is certainly one vehicle to get there. And so polymers are also low power. And we can see from this chart here that goes back to, I guess it's 20 years, 2000. And in 2000, we were using lithium niobate, which is in the sort of 40, 50, 60 volts to drive those lithium niobate modulators. And then we transitioned in the mid 2000s from lithium niobate to indium phosphide. So we've seen a lot of indium phosphide modulators used in the network. And in the last decade or so, we've transitioned also with indium phosphide and as well silicon. We've seen silicon modulators used in the network. I think as we look forward, we have to transition to something that's less than 1 volt. And electro-optic polymer modulators not only can provide the speed, but they can get the power consumption down and really have an effect on system architecture design and transceiver design by getting the voltage levels less than 1 volt. And so as we look at this graph, which has commercial progress and developmental progress, which seems to trail it by a few years, it's going to be really exciting as we look forward to sub 1 volt low power electro-optic modulator technology. And so what we've been working with is different types of parties, but we're also working with different types of companies that design different device types to test our electro-optic material. In this particular case, this was a post-deadline paper at ECOC 2022 that shows the world record in terms of performance with reliability and stability charts, as you can see in the top left-hand corner. But what we actually achieved here is Mach-Zehnder modulators, thermally stable, 140 gigabaud PAM4 transmission with sub 1 volt drive signals. And these things are less than 1 millimeter long. So this is really exciting. Small footprint, high speed, low voltage, low power consumption, really exciting stuff. And also we worked with not only Solorix in the last slide, but Polariton in this slide. And they were doing a greater than 500 gigahertz bandwidth using plasmonic to plasmonic links. And if we look at the yellow box in some of these complicated different diagrams here, we can see the use of our electro-optic material in their plasmonic modulators. This is also a post-deadline paper at ECOC 2022 with world record performance. The point where I brought these two slides into this presentation is this is third-party review. These are two different types of electro-optic modulator devices that use our polymer material and both achieved world record performance. And this is really exciting. So it's not really the device type, it's the material that's really leveraging high performance devices. And this is exciting for us. So to summarize, I've talked about a lot of different things in this presentation, from the materials to the use of foundries and fabrication, high-speed design and packaging. We have a powerful patent portfolio, and we're addressing huge, I guess, optical interconnect, data center interconnect, high performance computing type markets using that technology at 1310 and 1550. And we're solving a lot of the big issues that the hyperscalers are seeing in terms of scaling up, trying to keep the power under control and dealing with the increased traffic. And so I want to finalize on this slide, and the 4 takeaways I started with is, well, one of them was we have unique polymers, and we can see here that polymers are really unique, and they really are enabling the technology for ultra fast and ultra power solutions in terms of optical engines that go into transceivers for the internet, for the optical network. And what we want to do here is the reason why we are really excited is we want our polymers to become ubiquitous, just like organic LEDs, just like the polymers in organic LEDs. And to do that, you have to be able to scale in volume quickly and efficiently. And so our polymers, as you can see here, we're working with big silicon foundries. We are really excited with that. And we're partnering with the foundries, but also partnering with packaging and transceiver partners. And our polymers are clearly pluggable compatible because they're also very small in size. And I believe, thank you very much. And I'll end with, we've made some unparalleled progress in the last year. We've got some ultra fast technology, and we want that technology to be ubiquitous. Thank you very much.
Thank you so much, Michael, for sharing how polymers can boost PIC speed and power. I'd like to close with a couple questions, and to remind everyone in the audience, if you haven't already, you can type your questions and you can type your comments into the conference chat. And no worries, if you haven't been answered yet, you will be reached via email at a later date. Michael, you mentioned the importance of kind of breaking through that green wall, reaching a single lane link speed. What does that do for you guys in terms of breaking that wall? What does that open up in terms of what you want to accomplish with those electro-optic polymers?
No, it's if you can take the optical device speed, which a lot of optical devices today run 30, 40 gigahertz in bandwidth. You can double that or even triple that. So let's say 100 gigahertz 3 dB bandwidths. You run in 150 gig or 300 gig PAM4. The industry today, I just attended an industry workshop the last couple of days, and I was the ECOC conference just a month ago, are talking about next generation of 200. We have a technology that's already, allowing people to implement not only 200, but even faster systems. And you can see from some of these graphs, it doesn't just stop with a 200G line rate. People are looking at what to do next. And so what we have here is a technology that not only breaks through that green wall, but actually it's not only for this or next generation, but it's going to be here for a decade or more. We have a technology that's got legs, and it's future-proofing high-performance optics. On one hand, I think that addresses your question. But the good news is if you have optics that goes a lot faster, that gives the system architects a little bit more freedom in how they want to design their line cards, their electronics. Do they go with less power consumption? Do they look at options of going NRZ as opposed to PAM4? Or are they forced to go to PAM8, PAM16, or QAM? So it gives the architects a little bit more freedom in how they want to design their systems. And maybe they want to design their systems to be super low power consumption. We're just giving that option. And I think it's going to be really important as we move forward.
You mentioned standardizing hybrid PICs. There's the importance when you're working with different foundries to mix and match. When you're speaking to those roadmaps, do you see a future where maybe there's less mix and matching and maybe a little more standardization across foundries, or is that maybe pushing it a little too far?
Well, you have to think about what the foundry's business is in the first place. It's running wafers, and generally it's running CMOS wafers. This is their business. Foundries are interested in silicon photonics because we offer an opportunity for them to run more wafers, quite simply. And they look at our business not only from the comm standpoint, but from some of the other market verticals like automotive and LiDAR and displays, consumer products. They see if we can use photonics, PICs into those markets, then there's going to be a lot more wafers running these foundries. And so I think as they see more wafers being run, they're going to be more amenable to mixing and matching technology in order to allow them to run more wafers. And you can see here, there's a number of different sort of hybrid technologies that are actually helping silicon photonics and helping indium phosphide become more competitive. And I think, when you're put yourself in a foundry job or the foundry position and you have an opportunity to double or triple your wafer volume, you've got to take a look at that seriously and take a very close look at implementing some of these new technologies. The good news about what we have is it's already foundry compatible. So from our standpoint, that's really exciting.
Awesome, thank you. That we have time for one more question before we take off here. And one of my favorite sayings is the best ability is availability. So talking about those roadmaps, especially in the short term, what are some of your focuses or targets to specifically optimize or commercialize, standardize, basically any of them, these electric optic polymers?
So you saw from our foundry slide that it takes time working with foundries, and we over the last year we've made a number of different announcements of working with different types of foundries. We said we're expecting results later this year and then next year, and that's we expect 2023 to be a great year. We're already getting wafers back, as I already showed in this presentation, and it's as the wafers come back, you have to work with your other partners, your packaging partners and your transceiver partners, which means, I have to be careful because we're a public company and I have to not step over guidance, but 2023 is going to be a really exciting year for us. And I think that probably addresses your question.
Awesome, Michael. Thank you so much for sticking around for an extra couple minutes to answer some questions. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 2023 Photonics Spectra Conference. Lastly, thank you again, Michael Lebby, for presenting how electric optic polymers boost PIC speed and power efficiency.
Oh, thank you very much.